Hey y'all, so we learned what minerals are: inorganic, naturally occurring, crystalline solids that have a definite chemical composition and a repeating chemical structure. So what we're going to get into now is mineral identification. And I'm going to show you a whole bunch of different things. We're going to take a look at color, luster, streak, mineral cleavage and fracture, how mineral breaks or doesn't. We're going to take a look at the mineral hardness, and we're going to take a look to see if minerals react with hydrochloric acid or not. Now, you're going to be doing a lot of this in class, so I'm just going to go ahead and show you what these properties are, and then it's going to be up to you to apply them later on. So let's go ahead and take a look. All right, so one of the first properties that you're going to take a look at, they call it the first but the worst, is mineral color. And as you can see from these minerals, a lot of them have very similar colors. There's something like this that we can describe as kind of clear or white. And then there's something like this that definitely has a clear property to it. We can call it clear or white. And then there's ones that are unique, and it's kind of like, it's like this, which is kind of bluish, greenish, kind of green. Now, a lot of this is subjective depending on how you see colors. If you're colorblind like me, it's going to be hard to tell the difference between blues and greens. I guess this is mostly green. But it still is a pretty good property to start with because it can help you narrow down some of the minerals that you're going to take a look at. So what you'll do for this is you'll just simply pick up a mineral and you describe its color. Here's another one. We'll call this one gray. Gray or silver. I'll call that one gray. And you'll just go through the rest of the minerals and you'll put down what color it is. So the other property you're going to take a look at is streak. It's a little bit better than color because it'll show you the color of the mineral when it's ground up. And to do that, you're going to use these tools right here. They're called streak plates. We have one dark colored one and one light colored one, just in case you want to look at light streaks versus dark streaks. And here's one that's pretty easy to see. I have this mineral here, and I'm just going to grind it up on here, and we see that it left a clear dark color there. You see that right there? And that color is kind of gray right there. And here's another one right here that I can do, and it leaves kind of a tan color. Now, some minerals will leave a white streak, so I'm going to use the lighter color or the darker color streak plate, and there's that white streak. So all you have to do is take the mineral and just rub it up against the streak plate there, and it will tell you what the streak is, or what the color of the streak is. Some minerals won't leave a streak. So if I take this mineral and I grind it up here on the streak plate, it's not going to leave anything because the mineral is harder than the streak plate, and this isn't strong enough to break apart the mineral and grind it up. So some minerals will leave no streak, and you'll just record no streak. Now, another observation you're going to make is what's called crystal form, and that's the shape of the broken mineral. Now, all these minerals are broken, every single one, so you're not going to have to break anything. And if we take a look at this one here, there's no pattern to how it breaks. It's just all kind of random. The outside shape of it is random, and there's no clear pattern to it. This one here has a crystal shape. It looks like a rhombohedron, and so we're going to call this one rhombus. And you'll have a chart available to you to compare the crystal shape and determine the shape of each sample. Now, another thing that you're going to take a look at is how a mineral breaks, which is referred to as either cleavage or fracture. If a mineral breaks in a pattern, we call that cleavage. If it breaks in any random assortment, we call that fracture. Here's a mineral that has fracture. It doesn't break in any discernible pattern. You break it and it just shows up in any old way it wants. But here's one that's kind of cool. I take this and I take this hammer here and I just give it a tap here to break it a little bit. There we go. And when I break it, it's always going to break in boxes, no matter what I do. And even these little tiny pieces right here, they're all in boxes. So we call this a cubic cleavage, cubic, because it's always going to break in cubes, which is kind of cool. And here's another one. If I take this one, here's that one that started out as a rhombus. I'm going to take it, I'm going to smash it, and look at that. I'm going to keep on getting little rhombohedrons. So rhombohedri, or maybe for plural, I'm not sure. Rhombohedrons right there. So anytime I smash this, no matter how many times I smash it, it's just going to produce these little rhombohedral patterns all over the place. And that is the fracture, the cleavage of this mineral. All right, so another test that we're going to perform is called the acid reactivity test. Some minerals will react in hydrochloric acid and others won't. So if you just put a few drops, a couple of little drops of acid on the sample, then you'll see it fizz just like that right there. It'll kind of bubble up quickly and then it will dissipate. And other minerals, like this one right here, if I put some acid on there, it'll just kind of run off without reacting. You won't see any fizzing whatsoever. So we have this one here that did react, and we have this one here that doesn't react. There's our acid reactivity test. So another thing that we could take a look at, just wipe this away, is how the mineral looks, not in terms of its color, but in terms of how it reflects light. We call that luster. There are a couple lusters that we're going to get to know. There are the lusters like this, where the sample looks like a piece of metal, and we're simply going to call this metallic. And everything else is non-metallic. So these two are the same exact ones. We say that these are metallic. And all these other ones over here that don't look like a metal, well, they're all non-metallic, but they all reflect light a little bit differently. Like this one right here is super shiny, and we're going to call that one glassy. And then there's this one here that's kind of shiny, but not as shiny. It doesn't look like a piece of glass like this one here. So we'll just call this one pearly. Call this one pearly. Now there are other ones that don't reflect any light, and we call those dull because they're just dull. They don't have any shine property to them whatsoever, any reflective property to them whatsoever. So there's your dull ones. Here's another glassy one real quick. This one's different than this one. And here's another pearly one right here. Here's another pearly one. It reflects light. It's kind of shiny, but not as shiny as these guys over here. So we have our metallic ones, our glassy ones, we have our pearly ones, and then we have ones that are just dull because they don't reflect any light. Another test that you're going to perform to help you identify the minerals. This one's a little bit tricky. It's called the hardness test. Now, I want to be clear about this. The hardness test does not refer to if you can break the mineral or not. I can take this hammer and I can break any of these minerals with enough brute strength. They say that diamond is the hardest mineral that's out there. I can use this hammer and smash a diamond to bits if I wanted to. That's not what they're talking about when they talk about mineral hardness. What they mean is, can the mineral be scratched? And the reason why diamond is the hardest mineral is there's no other mineral on earth that will scratch a diamond, but a diamond will scratch every other mineral. So the idea is this, is I'm going to figure out how hard these minerals are on a scale of 1 to 10 with some known substances. What known substances? Well, your fingernail. Your fingernail has a hardness of 2.5. So if I can take a mineral and I can scratch my fingernail with the mineral like that right there, well, then the mineral is harder than my fingernail. So it has a hardness of at least 2.5. Now you don't need to memorize the hardnesses of these objects, but we have a 2.5 for your fingernail, 3.5 for the penny, 5.5 for the glass plate, and 6.5 for this steel block. And what we're going to do is we're going to test these minerals up against these known substances of hardness to kind of get an idea of how hard they are. Here's an example. Here's another one. I'm going to take this mineral here and I'm going to see that it will easily scratch my fingernail up. No problem. And then I'm going to take it on the penny and I'm going to try to scratch the penny. And it easily leaves a nice scratch right in that penny. So that means that the hardness of this mineral is at least as hard as the penny. The penny's hardness is 3.5. So the mineral's hardness is at least the 3.5. It's going to be a little bit more. I'll try it on this glass plate here. Now, I don't want to sit here and break the glass or anything. It doesn't take much force. But I'm scratching this glass plate, and if we take a look at it on this darker surface, there's no scratches in there. And if I try that again, we can hear it going, but it's not leaving any scratches in the glass. Now the glass has a hardness of 5.5 and the penny has a hardness of 3.5. So the hardness of this mineral is somewhere in between. So we can say that it's between the penny and between the glass, or we can say that its hardness is about 4.5. Again, if the hardness of the penny is 3.5 and the hardness of the glass is 5.5, then that means because this mineral scratched the penny, but not the glass, that its hardness has to be somewhere in between. So we'll call it a 4.5. Now, if I take another mineral, like this one right here, we'll see that it will scratch my fingernail pretty easily. Scratches it up pretty easy. And we'll see that it should scratch the penny pretty easily. There's a big scratch right there. And maybe we'll see on this one here that it easily scratches the glass as well. So this is harder than the glass, so its hardness is at least a 5.5. And here's that steel block. And if I try to make a scratch in the steel block, we'll see that it's scratching up that steel block pretty nicely. So what that means is that its hardness is harder than that steel block. The hardness of the steel block is 6.5. So for this mineral, I'm going to put 6.5 plus or greater than 6.5 because we know that this is a fairly hard mineral. Some of the minerals that you test will not scratch your fingernails. Some of the minerals that you test will scratch the penny, but not the glass, and all the way on down. It's going to be the trickiest part of this whole thing. The last thing that you're going to test for is a mineral's density. A lot of minerals look very similar. They have a lot of very similar properties. However, they are different. And determining the mineral's density will help you really find the difference from one mineral to another. How do you find a mineral's density? Well, you need two things in order to calculate a mineral's density. You need the mass of the mineral and the volume of the mineral. Now, to find the mass of the mineral, it's pretty simple. All you have to do is take the mineral and put it on the scale here, and it will tell you the mass. And right here, the mass of this one is 16.5. Now, we need to find the volume of the mineral. To find the volume of the mineral, we use what's called water displacement. I have a graduated cylinder here, and in that graduated cylinder, I have some water. It's about 30 milliliters of water. And when you do this, you want to be pretty precise. So I'm going to call it 30 milliliters of water. And the idea is that I'm going to put this mineral in the graduated cylinder, and the water is going to rise to whatever volume this mineral is. Now, you already know this idea. If you have a glass full of water and you add some ice, the water overflows in the glass. Well, it's going to be displaced by the volume of the ice that you put into it. Same thing with this. The water will rise to whatever volume this mineral is. So if this is at 30 and I slide the mineral in, and I read the new volume and it goes up to 36, what that means is that the volume of this mineral is 6 milliliters. And then what I'll do is I'll take that original mass that we found of 16.5 grams and I'll divide it by that 6 milliliters, and that will tell me the density of that mineral. And you're going to do that for all the rest. Now, you don't have to worry about these samples fitting in the graduated cylinder because you're going to be using the computer simulation. It's going to be pretty easy because it'll all fit in there pretty easy. But there is an electronic balance, and you'll have to drag the mineral onto the electronic balance and find the mass of each one. And you'll have to drag it into the graduated cylinder to find the volume of each one. So all these tests and observations are done to help you identify these minerals. Now, we're not going to identify all the minerals on the palette that we were looking at earlier. You're only going to identify 7 of them. We're going to do a couple of them together. And you also don't need to memorize the names of the minerals. But what you do have to know is how to use the properties that you're gathering in these tests and observations, and how to use a flowchart to identify the minerals. So we'll go through a couple of examples of that as well. But once you have all the properties, the color, the luster, the streak, the cleavage and fracture, the hardness, the density, and the crystal shape, then all that are clues that you're going to use to identify the minerals.